Hi everyone. In this lesson we're going to go over vector spaces. Now in calculus you've probably already seen vector spaces in R2 and R3. Recall R2 is just a Cartesian plane like x comma y. That's how you would represent points in R2, and R3 is when you add a third component like x comma y comma z. Now recall that if you're given a point like x comma y in R2, you can think of that point as defining a vector, and we use this notation. We write u, or v in this case, equals x comma y. Now instead of thinking of this as being a point, we think of it as a vector, meaning that it represents a line segment beginning at the origin 0, 0 and ending at the point x comma y. And we put a little arrowhead at the point x comma y like we have illustrated down here. So right here this would be your vector. So that point right here, that's the point x comma y in the Cartesian plane, or R2. Now a vector has two components. It has a direction defined by this point, so the direction would just be the direction the arrow is pointing in, and a magnitude, which is the length of the vector. Now by the Pythagorean theorem, the length of this line segment right here is just the square root of x squared plus y squared. And we use the notation, the length of the vector, that's the notation we use right here with these double bars around v, and that would just be the square root of x squared plus y squared. So the distance right here, that distance, the length of that vector, is denoted like this. Okay, so that's your length notation or magnitude notation for a vector. Now in R2 you'll sometimes see the direction defined as the angle theta, like we have illustrated right here. So you see you have your vector, and then the angle defined from the x-axis to the vector, we call that theta. Sometimes you'll see people refer to this theta as being the direction of a vector. Now that's only valid in R2, not in any other Rn space like R3 or R4. And you can use this rule down here to find the angle. So you just have to plug in the x and y values of your vector into this formula here, paying attention to whether the y coordinate is positive or negative, and this will give you back that angle. Now also take note that in R2, if we calculate this angle, we can write the vector x comma y like this right here. The x coordinate will be the magnitude of v times cosine theta, and the y coordinate is the magnitude of v times the sine theta. And that's because if we complete a right triangle up here like this, you see that distance is going to be the magnitude of v, which is the length of the hypotenuse here, times the cosine of theta. And similarly, this distance right here is going to be the magnitude of v times the sine of theta. Right, and that just comes from basic right triangle trigonometry. Now in R3, right here we have a typical vector in R3, say 2, 3, 5. Notice that's in R3. We have 3 components here to this vector. And we would visualize this vector as we have right here. So right here we have the vector, that's the red arrow right here, 2, 3, 5. Notice we have an x-axis, a y-axis, and a z-axis here. So you would think of the x-axis as sort of coming out of the page or out of your computer screen. And also notice that we have a vector right here in the xy plane like this. That's actually the vector 2, 3. That's this portion of the point up here. So that would be the vector 2, 3 right here. And then we go up 5 units in the z direction, and then we draw our arrow from the origin out to the point 2, 3, 5, and that gives us our vector. So this would be our vector right here. And here's some notation that you should be aware of. Sometimes it's easy to confuse a vector with a point in Rn because they use similar notation. So sometimes in order to differentiate a vector, you'll see this notation used. You see, so you've replaced the parentheses here with these angled brackets. Or sometimes you'll see the v written with a little arrow over top of it. That will indicate a vector. Or sometimes you'll see this written in bold font. I don't have bold font used throughout these notes, but sometimes you'll see that written in a bold font to indicate a vector. Now here we have some basic vector operations in Rn. So recall that Rn is just defined to be the set of all what we call n-tuples, like this. So they're just a list of numbers, x1, x2, xn. So you would have n of these numbers listed out. Just like in R2, you'd have 1, 3, for example. That would be a point in R2. Or as we've seen before, 2, 3, 5. That would be a point in R3. Now, if we let u be a vector right here in Rn, so we have n components here to it. Notice u1, u2 out to un. And v be another vector, v1 through vn. Then we define vector addition, scalar multiplication, and subtraction of vectors like this. So we would define the addition of these two vectors to be this vector that we have right here, where we just add the components. So notice we just take u1 plus v1, that's going to be the first component of our sum vector. u2 plus v2, that's the second component, and so on. So that's simply how we define vector addition. We just add the components of our vectors right here. Scalar multiplication is defined like this. So when we talk about a scalar, in our case that's just going to mean a real number. But in other settings it could be like a complex number or some other object. So a scalar k, you can think of that as just being a real number in this case, times a vector u. What you do is you just take that k and multiply it by each component of the vector u. So you just take k times u1, k times u2, and so on, and that's what you get. So that's simply how we define scalar multiplication. And then vector subtraction, we would just define it to be as follows. So u minus v, well, we're just going to subtract each component. So you notice we have u1 minus v1, u2 minus v2, and so on, which you can also think of as being u plus negative 1 times v. This will come in handy later on, this observation here. Now, in R2 and R3, we can visualize all of these operations pretty easily, like what we have listed down here. So notice that in R2, here's how vector addition is represented graphically. If I take two vectors right here, u and v, and we add them, then that's equivalent to completing a little parallelogram right here using u and v as being two sides of the parallelogram. So you complete it, and then the sum vector will just be the vector going from the origin out to the furthest corner of that parallelogram. So that's what vector addition is in R2. And it's also the same in R3 as well. It's just that this parallelogram here would be lying in 3 space. Now, as for scalar multiplication, you can visualize scalar multiplication like this here. If we take a vector u, now I use the letter u here instead of v. If you take u and you multiply it by a scalar k, in this case k would be bigger than 1 for this graphic here, then what that's going to do is just stretch the vector like this. So in this case, for example, the blue vector looks like it's almost about twice as long as that red vector is. So this blue vector might be like 2 times u, for example. Now if k is negative, like we have right here, then what that's going to do is flip your scalar multiple in the opposite direction. So right here we would have k times u for k negative. And also if k is between 0 and 1, so like 1/2 for example, well then that vector might look like this. So here would be u, so k times u might be this vector right here. Notice it would shorten the length a little bit, but it would still be pointing in the same direction as u. So this one right here might be k times u for k between 0 and 1. Now vector subtraction can be visualized like this. So in R2 or R3, right here we have a picture in R2, the Cartesian plane. If this is your vector v right here, and this is your vector u right here, then u minus v is going to be this vector right here, where notice if we sort of translate it, we can think of it as being the vector pointing from the tip of v towards the tip of u. And the reason this is because if you look at what negative v represents, negative v would be like right here, say. So for example, that would be negative v. And u minus v is going to be u plus negative v. So if you complete this parallelogram between negative u and v, you see, if you complete the parallelogram here like we did with addition, and then you add u plus negative v, you see you get this vector right here. So that's u minus v, which is equivalent to thinking of it as being translated over here. So you just think of it as being this vector, as I said before, pointing from the tip of v towards the tip of u. So that's where we normally think of u minus v as being. However, keep in mind when we draw this, this isn't actually u minus v right here. U minus v actually lives right here because its base starts at the origin and points out in this direction. But oftentimes we think of it as being this dotted vector segment over here. So that's how we visualize u minus v. Now we also have this definition here. The norm of a vector, which is also representing its magnitude or length, is defined like this. So here is the notation we use for the norm of a vector u, and it's simply the square root of u1 squared plus u2 squared plus ... out to un squared. Now this is for vectors in Rn, keep in mind. We're going to generalize this later on. So this is what we define the norm or magnitude or length of the vector to be. So for example, find the magnitude of the following vectors right here. For example, this one is in R2, 4, negative 2. So the norm of that vector or length is just the square root of 4 squared plus negative 2 squared, which is the square root of 20. This vector right here is in R3, and so its norm would just be the square root of 2 squared plus 3 squared plus negative 2 squared, and that is just the square root of 17. So that's the length or norm of this vector. Now let's define unit vectors. Now a unit vector in Rn is just a vector in which its length or norm is equal to 1. So that's what we call a unit vector. And we have this following proposition. If we're given a non-zero vector u, like this that we have right here, then the vector where we take u and multiply it by 1 over its norm, that's going to be a unit vector pointing in the same direction as u. And we have a proof of that right here. And maybe before we look at the proof, just note one thing. What I'm saying here is that, if we have a vector, so say we have a vector right here like this. So say that length is, for example, 3. The length of this vector right here is 3. If we take 1/3 times the vector, that's going to be a unit vector, so it would be this vector right here maybe. And this would be of length 1, and it would be pointing in the same direction as u. So that's what we're creating when we take 1 over the norm of u times u. It's just going to be a vector pointing in the exact same direction as u, but this vector is going to have length 1. And here's the proof of this result. If we let k be 1 over the norm of u, notice that that's going to be a positive number. Then note that if we look at the norm of k times u, that's going to be this quantity right here by definition of the norm. And notice we can factor out a k squared. We get this result right here. And k is 1 over the norm of u. That's what it's defined to be right here. And the norm of u is just the square root of u1 squared plus u2 squared out to un squared. And when we take 1 over the square root times the square root, of course, these cancel. And you end up with just 1. So it's a pretty simple proof. Let's take a look at this example right here. So let's find a unit vector, a vector of length 1, pointing in the same direction as these two vectors right here. Alright, so for part A, all we have to do is take this vector and multiply by 1 over the norm of u. Now let's note that the norm of u in this case is going to be the square root of 34, you see right here. Because the norm of u for part A, right, just take note that that's going to be the square root of 5 squared plus 3 squared. And of course that is the square root of 25 plus 9, or 34. So u divided by the norm of u is going to be 1 over the norm of u, which is 1 over 34, times the vector u. So right here we have that right here. And then just multiply this number. This is your number k right here. Multiply then that into the 5 and the 3. And you get the vector 5 over root 34, comma 3 over root 34. And that is your unit vector. And it's very easy to verify that this vector right here has length 1. For example, if we took the square root, if we evaluated its length, of course we're going to get back 1. Notice if I take 5 over root 34, square it, plus, and then 3 over root 34 and square it, well, let's see, that's just going to be the square root of 25 over 34 plus 9 over 34. And of course you get the square root of 34 over 34, which of course is 1. So that proves that this vector that we created here has length 1. And then for part B, we would do the same thing right here. But just note for part B, the length of u, right here, the norm of u, is the square root of 35. That's because 3 squared plus negative 1 squared plus 5 squared is 35. So just note, here I'll write it out, just note in this case the norm of u is going to be the square root 3 squared plus negative 1 squared plus 5 squared, and that is root 35. So 1 over root 35 times your vector u, you just multiply this against each component. You get 3 over root 35, comma, negative 1 over root 35, and there should be a comma right there. 5 over root 35. And that's your unit vector that points in the same direction as the vector 3, comma, negative 1, comma, 5. And so that's a little bit about the vector spaces R2 and R3, along with the vector operations on them. Now, what we're going to do next is generalize the notion of a vector space. So a vector space is a way of placing a mathematical structure on a collection of objects in such a way that certain properties have to hold. And this structure is just a generalization of all of the properties that we saw previously with respect to the vector space Rn, where we added and subtracted vectors and took the norm of them. So we're just going to generalize those concepts for other spaces. Now, the study of vector spaces in mathematics is very important, and it yields a lot of useful results, one of which is the study of Fourier series, which is a very important theme in the study of digital and analog communication systems. So if you're an electrical engineer, for example, you most certainly would study Fourier series. So here's our definition for a vector space, and this is going to be a real vector space, because the scalars that we're going to be using are going to be taken from the real number system. So a vector space V over the real numbers is a collection of objects which we call vectors, along with a rule for how to add them and how to perform scalar multiplication with them. Now, in order to be a vector space, you're going to have all 10 of these properties being satisfied. So let's just run through these here quickly. The first property that we need to hold is that if you take two vectors, u and v, that are in your vector space and you add them, you get another object in your vector space. So we then say that addition is a closed operation. If you take a scalar and you multiply it by the vector u, using whatever rule you have for scalar multiplication, then you must also get another object back that's in your vector space. So we say scalar multiplication is a closed operation there. You have to have commutativity holding, so u plus v equals v plus u, that must hold. You also have to have associativity holding, so u plus v plus w is the same as u plus v plus w. There also has to exist a zero vector in v, in which v plus the zero vector gives you back v. So you must have this zero vector in there that when you add it to any other vector, you just get back the same vector again. And this zero vector is called our additive identity, or the zero vector. And later on, we will prove that that is actually a unique vector in any vector space. So there is only one vector that will satisfy this property. Also, for every vector u in your vector space V, there must exist a vector w in V, such that u plus w is equal to 0. And we then denote that vector w as being negative u. So there has to exist a vector w in which u plus w gives you back the 0 vector for every vector u. Now you also have a distributive property for scalar multiplication against vector addition, and it goes like this. Any scalar times u plus v equals k times u plus k times v. And then we have another property here. You have a distributive property for scalar addition. So if you take two scalars, k and l, then k plus l times any vector u is going to be k times u plus l times u, so that must hold. And then you also have an associative property for scalar multiplication. K times l times u is k times l if you multiply those together first, and then multiply by the vector u. Now keep in mind, this is can be a little confusing here at times. These are actually different dots here. This dot right here is actually real number multiplication if k and l are real numbers. And this dot right here actually represents this dot right here where you're defining whatever your scalar multiplication is. So these actually mean two different types of multiplications. It gets a little confusing at times because of that. So you just have to understand what the context of your multiplication is. And finally, the last property that we have to hold is that for the number 1 times any vector u just gives you back u for the scalar 1. So keep that in mind as well. All right, so for something to be a vector space, we need all 10 of these properties must hold. Now here's something you need to be careful about when you're dealing with notation. When you're working with the 0 vector, which is denoted like this, of course keep in mind that that is different from the scalar 0 or the real number 0. For example, in R2, the 0 vector would be the vector 0, 0, like that. And of course the number or scalar 0 is just 0. Now oftentimes you might see the vector dropped off of this 0 vector here, and so you might see written something like 0 plus u right here where u is a vector, and so you have to realize that the 0 here is actually referring to the 0 vector like that. So sometimes you'll see people drop off the arrow that's over top of the 0, so you have to just understand what the context of your problem is. Now let's take a look at this example here. So recall that Rn is just the set of all n tuples consisting of points x1, x2 out through xn. And if we let u and v be two elements in Rn, thinking of them as vectors, and k being a scalar, then remember this is how we define vector addition right here, and this is how we define scalar multiplication. Now let's verify that with this notion of addition and scalar multiplication that Rn actually defines a vector space. In other words, it satisfies all of those properties that we saw in definition 4.1.95. Now keep in mind one thing here. This gets to be a little confusing at times. You've actually got two different additions going on here, even though you have the same addition symbol here, and you have two different multiplications going on as well. So you notice you have an addition symbol here. That means vector addition. And you have an addition right here. That actually means just number, regular number addition. So keep in mind that these two plus symbols actually mean different things. And also right here, we don't have a dot here, but you could put a dot right in between that k and u1, and then those two dots would actually mean different things as well. This would mean scalar multiplication of a scalar against a vector, and this dot right here, if we put one right here, that would just mean multiplication of two real numbers. So keep that in mind. And that's why sometimes you'll see people use different notation. Like down here, sometimes you'll see people write U and then use a different symbol for addition here than they do over here. And the same thing with scalar multiplication. Sometimes you'll see a little different notation here, like a dot with a box around it, and over here you have a dot, just indicating that these two multiplications are actually different multiplications. Now let's verify that Rn actually satisfies all of those properties in definition 4.1.95. Now, because we have 10 properties, we're not going to go through all of them. They're fairly easy. Let's just go through properties 4, 5, and 7 from that definition. So property 4 makes this statement. We need to verify that u plus v plus w equals u plus v plus w. So you see how we move the parentheses. Alright, so if we start out with this right here, notice that we can write it component-wise like this. So here's our definition for vector addition. So notice that we just take u1 plus v1 plus w1, comma, u2 plus v2 plus w2, comma, dot, 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 and we go all the way out to un plus vn plus wn. Now, if you look at one of these pieces, like this one right here, look at one of these components, this is just regular number addition. These are just real numbers, u1, u2, v2, and w2. And so certainly real number addition satisfies an associative property, so you can move these parentheses over to the u2 and v2 like we have right here, and you can do that for all of them. And so what you end up with is this. You see how we move the parentheses for each one right here, here, and here. And then this term right here that is then going to be u plus v with the parentheses around the u and the v plus w. And that proves it. Now for property number 5, we need to show that a zero vector exists. Well, we just define the zero vector to be 0, 0, dot, 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 0. So notice that if we take any vector v and we add this zero vector to it, by definition of addition, it's going to be v1 plus 0, v2 plus 0, dot, 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 vn plus 0. And that's just v1, v2 out to vn. And that's just v, so we do get back v. So in other words, v plus this zero vector that we defined is just v. And then for property number 7, if we look at k times u plus v, where k is a scalar, notice u plus v, we can write that like this right here. So we just add the components together, and then we just multiply the k into each term, and we get this right here. And then we can distribute the k. So notice that this term right here is k times u1 plus k times v1, and the same for all of them. And then this is just by definition ku plus kv. And so there you go. We verified that you can distribute the k to the u and the v, and we end up with this. So that verifies that property number 7 holds. And all of the other properties can be proven in a similar manner. They're all pretty easy. Let's take a look at another example. So here's a little different type of vector space that you haven't seen before. Let's consider C01, which denotes the set of all continuous functions with domain 0, 1, 0 to 1. Let's verify that this set of functions, the set of all continuous functions on the interval 0 to 1, with these operations for addition, f plus g is just f of x plus g of x, and k times f is just k times f of x. Let's verify that with these two operations, this set forms a vector space. So technically we have to go through and verify all 10 of those properties hold. Now we're just going to verify 2 of the properties here, and then the other ones are very similar. So we're going to verify properties number 1 and 4. So if we're given 2 continuous functions, f of x and g of x, which are continuous at a point, it is also a result that f of x plus g of x is going to be continuous at any point c. Therefore, if f is continuous over the interval from 0 to 1, and g is continuous over the interval from 0 to 1 as well, then f plus g is going to be continuous over the interval from 0 to 1. So therefore, addition is a closed operation. So in other words, we've just reasoned that if you take any 2 items from C01, if you take any 2 functions from here, when you add them, you will get another function that is back in here. In other words, when you add 2 continuous functions, yes, you do get another continuous function. Now for property number 4, we have to show that an associative property holds. So if we look at f plus g plus h of x, by definition that is this right here. And by definition of addition here, what we have in the parentheses right here is just g of x plus h of x. Now what we have here is this addition is just real number addition right here. We're adding these real numbers, f of x, g of x, and h of x. So by the associative property for real numbers, we can move these parentheses with the f and g, and we get this result right here, which is just f plus g with the parentheses around it plus h of x. And there you go. And also, we don't have it written down here, but if you wanted to verify property number 5, that there is a 0 vector in this vector space right here, well, what do you think you would define the 0 vector to be? Well, it's pretty easy to realize that we should define the 0 vector to be just the function 0, right? Then f of x plus the function 0 for any x is just going to be f of x. So the 0 vector is just the constant function 0. Here's another example. Let's take a look at something that is not a vector space. So let's let V be R2 with addition and scalar multiplication defined like this. So we take u plus v, we define that to be u1 plus v1 comma 1. So it doesn't matter what the second component of the u and v are, we just say u plus v is always going to be 1 right here. And then scalar multiplication is just defined like we usually do, right here. Let's prove that V does not form a vector space. All right, so you have to think through about which property is not going to be satisfied. Well, property number 5 is not going to be satisfied. We're not going to have a 0 vector here. For example, if we take u, which is, let's say it's 1, 2, there does not exist any vector where if we add u to that vector 0, we get back u. Because no matter what we try to define the 0 vector to be, say it turns out to be a plus b, Then if we look at u plus the 0 vector, well, by this definition up here, that's going to be u1 plus a. All right, that's fine. If a were 0, we'd get u1, that's fine. But the second component is always going to be 1, no matter what. And notice this 1 does not equal the 2 right here, if we let u be 1 comma 2. So no matter what we try to define 0 to be, to add it to u, we can never get back u again, because we're always going to get 1 in the second component. So there is no 0 vector, and so this cannot possibly form a vector space with these definitions for addition and scalar multiplication. The scalar multiplication is okay. That would be all right, but not this addition right here. That just doesn't work. Now let's take a look at some properties of vector spaces. This is another example. I'll let you work on that one. Just showing that the set of all 2 by 2 matrices with this rule for addition, notice we just add the components together, and this rule for scalar multiplication forms a vector space. So you can verify that all 10 of those properties hold. Notice that really this is just like, sort of like the R4 here really is what we're dealing with the standard notion for addition and scalar multiplication. Because even though we have it written like a matrix, you notice we could write each of these as just A, comma, B, comma, C, comma, D. And then this one would be U, comma, V, comma, W, comma, X. And really, it's just the same operations as we have on R4. And so, of course, this is going to form a vector space because R4, with the standard notion of addition and scalar multiplication, forms a vector space as well. Now here are some important properties of vector spaces. So if you're given a vector space V, the following will hold for all vectors u, v, and w in V and scalars k. So first of all, that 0 vector is unique. There is only one 0 vector that satisfies u plus 0 equals u for all vectors u in your space V. So there's only one 0 vector that does that. It is unique. Also, the vector negative u is unique. Remember, that's the vector that satisfies u plus, well, we have it written right here. U plus negative u is the 0 vector. So there is only one vector that does this for each vector u in V. Also, if u plus v equals u plus w, then v must equal w. Seems reasonable, but that's actually something we need to prove, because remember, this plus here does not represent our normal notion of addition. Of course, it's true for real numbers. If a plus b equals a plus c, then b equals c for real numbers. But remember, this addition over here is a totally different concept than this addition over here. So we actually have to verify this. Also, if you take the scalar 0 times any vector, you get back the 0 vector. And any scalar times the 0 vector gives you back the 0 vector as well. Negative 1, the scalar negative 1 times any vector u, is actually that vector negative u. And if a scalar k times u gives you the 0 vector back, then either the k is the number 0, or the vector u was the 0 vector. So one of these cases must hold. All right, so we're going to take a look at the proofs of A, C, and D, and then leave the rest as exercises. So for part A, we want to show the 0 vector is unique. So this is a standard proof technique here. If you want to show that something is unique, you're going to say, well, suppose I have 2 of them. Suppose 0 sub 1 and 0 sub 2 are both 0 vectors. We're going to argue that the 0 sub 1 equals 0 sub 2. That's what we're going to argue here. Now let's take note that if 0, 1 and 0, 2 are both 0 vectors, then of course we have these two equations holding. 0, 1 plus u equals u for any vector u, and 0, 2 plus v equals v for any vector v. So then what we have from these two equations then is actually that 0, 1 plus 0, 2 equals 0, 2, right? So here we're treating this like the vector u. Okay, so this is like u and u. And also we have 0, 1 plus 0, 2 equals 0, 1. So here we are treating the 0, 1 like a vector u, and 0, 2 is the 0 vector. So obviously what we've concluded here from these two equations then is that, you see, we've got on the left-hand side we have the same thing, right? And on the right-hand side we have 0, 2 from this equation and 0, 1 from this equation. So therefore 0, 1 must equal 0, 2. So therefore the 0 vector must be unique. There's actually only one 0 vector. So that proves part A. Now let's prove part C. So for part C we have to assume u plus v equals u plus w, and we have to show that v equals w. So we start out with u plus v equaling u plus w, and what we'll do is we'll add negative u to both sides. Remember, that's the additive inverse of u. This is supposed to be the vector, so that u plus this vector, negative u, equals the 0 vector. All right, keep in mind that's what the negative u represents, and this is also written as just u minus u. Okay, so we add negative u to both sides, and then by the commutative property for vector addition, we can write this as u minus u, just move this u over here, and the v to the right, so we get this, and we do the same thing over here. Now you see we have u minus u, that's 0, and u minus u, that's the 0 vector here as well. So we get the 0 vector plus v equals the 0 vector plus w, and we get v equals w, and that's what we wanted to prove. Now for part D, we want to show that the scalar 0 times any vector u gives you the 0 vector. Alright, so what we do is we start out with any vector u, and here's how we're going to do this proof. So we start out with u plus, let's look at 0 times u. Now that's equal to 1 plus 0 times u. So you can sort of think of factoring the u away here. That's by property 8 of definition 4.1.95. Remember, that property said that if you have k plus l, two scalars k plus l times v, that you can write that as k times v plus l times v. Remember, that was that property. So the k is 1, the l is 0, and the v is actually u down here right now. So you see we can write this like this. Now this side right here, well, 1 plus 0 is 1, so we get 1 times u, and so we get back u. So you see we've concluded that u plus 0 times u equals u. So that's what we have right here. And now just add negative u to both sides, and you get that 0 times u equals the 0 vector, right? If we just add negative u to both sides here, right, you get u plus 0 times u minus u equals u minus u. This is the 0 vector. And the u and negative u over here, of course, they cancel, giving you the 0 vector. And we have that the scalar 0 times u equals the 0 vector, and that's exactly what we wanted to prove. All right, and so that concludes this video on vector spaces.